Hey everyone, I'm Bill Kinney, and this is my third video on that most beautiful of all mathematical subjects, complex numbers and complex analysis. In video number 1, we looked at integer powers of the imaginary unit I and saw some pretty amazing patterns. We saw that they always cycled between 1, I, -1, and -I. We plotted those in the complex plane. That's technically something called a cyclic group of order 4. Then in video number 2, we moved on to thinking about complex numbers as a real number plus another real number times the imaginary unit I, real part plus imaginary part times I. Both the real and imaginary parts were real numbers. We also saw how to think about those complex numbers visually as points in the complex plane, and also make a relationship between those points and their corresponding position vectors. In video number 3 here, what we want to talk about is complex number addition, also symbolically and visually, and I really want to put a big emphasis on the visual. As always, we want to focus on exploration, discovery, and hopefully joy in doing some pretty amazing math. Please comment, like, share, and subscribe to help the channel out. I'd really appreciate it. As usual, it's helpful to think in terms of examples. Let's let Z1 be a symbol that represents the complex number 4 plus 3i. So in this entire expression, the real number that's not next to the I is called the real part of this complex number Z1. It equals 4. The real number that is next to the I is called the imaginary part of this complex number. It equals 3. We're going to let Z2 be the complex number 2 plus 5i, and we're wondering, what does it mean to add Z1 and Z2? What should we get? The simplest thing to try, at least, even if it doesn't make sense in the long run, is to say, hey, let's just ignore the fact that I squared equals -1 and treat these things as two linear polynomials in I and add like terms. Question might be, is that useful? Is it interesting? That kind of stuff. We're going to see that yes, it's useful and yes, it's interesting. So go ahead and do it. The real part of the answer should be the sum of the real parts of the summands, Z1 and Z2, so I do 4 plus 2. And the imaginary part should be the sum of the imaginary parts in the original complex numbers Z1 and Z2. That's 3 plus 5. It's going to be the imaginary part of the answer, so I need it to be next to the I. Now simplify, we get 6 plus 8i. An immediate benefit of this approach is we see right away that the commutative property will hold. Z1 plus Z2 should be the same as Z2 plus Z1. And the reason is because the real numbers are commutative under addition as well. If I do this calculation, I get the exact same answer, 6 plus 8i. Symbolically, we could write that the real part of Z1 plus Z2, effectively by definition, is the sum of the real part of Z1 and the real part of Z2, and the imaginary part of Z1 plus Z2 is the sum of the imaginary parts of Z1 and Z2 individually. These two equations are true in complex analysis. As a big point of emphasis, I want to work us very rapidly toward thinking about complex functions of a complex variable, and even right now, in video number 3, I'm going to do that a little bit. I'm going to write W equals f of z equals z plus, let's take one of these particular complex numbers. How about the first one? 4 plus 3i, and say that I can think of this as a complex function of a complex variable. A complex valued function, w is a complex number, of a complex variable z. Z is the input, w is the output. You could call z the independent variable and w the dependent variable. F is the function name. I'm taking an input z as a complex number, and this formula is telling me take that z and add 4 plus 3i to it. This is our first complex function of a complex variable. I can evaluate this function at any particular number I want. In particular, I could evaluate it at z2. I could plug in 2 plus 5i, do the substitution in place of z right there, and then add 4 plus 3i to that. When the input is 2 plus 5i, the output is 6 plus 8i. It's another way of thinking about what we did up here, but it's going to have the benefit of helping us think about this geometrically in terms of what's called a translation of the complex plane. So let's go ahead and draw what's going on here now in the complex plane, not just in terms of the translation I just mentioned, but also in terms of what's called vector addition. Remember, Z1 is 4 plus 3i. I'm going to use different colors here. And Z2 was 2 plus 5i. Remember from video number 2 that I can associate these complex numbers with coordinates. The real part is the first coordinate and the imaginary part is the second coordinate. So Z1 can be thought of as the point 4, 3. Z2 can be thought of as the point 2, 5. And I can plot these two complex numbers in a plane that I'm calling the complex plane and visualize what it means to, in this case, add them. In the complex plane, you label the horizontal axis RE, you think of that as the real number line, and the vertical axis IM, purely imaginary numbers are on that vertical axis. Z1, 4 plus 3i, corresponds to the point 4, 3. I move to the right here 4 units and up 3 units. Z1 is going to be right there. Z2 corresponds to the point 2, 5. Move to the right 2 and up 5. Brings me right there. This is a way to think of Z1 as a point and Z2 as a point. I can also draw their position vectors. I can think of them as arrows, directed quantities. I can think of this arrow right here as being Z1 and this arrow right here as being Z2. So I've got two ways to think of complex numbers. Where is their sum? Let's draw their sum in green. Z1 plus Z2 is 6 plus 8i. So where is that? Move to the right by 6 and up by 8. That's going to bring me to right there. Make sure I've counted right here. 4, 5, 6, 2, 3, 4, 5, 6, 7, 8. That is going to be Z1 plus Z2, and I can represent that as an arrow. Now, is there a relationship between these arrows? Why don't you go ahead and, if you've never thought about vector addition before, take a moment to pause the video and think about it. Do you see a relationship between these arrows? Are you back now? I hope you saw that you could take this arrow, this vector for Z2, and translate it over this way and draw it starting at the head of Z1 here, this tip of this red arrow, and the ending point would be at the ending point for Z1 plus Z2. Or you could also take the red arrow for Z1 and translate it up here and draw it so that its tail, its base, is at the head of Z2, and its head will then be at also again the head of Z1 plus Z2. That was a lot of words. I hope it wasn't too confusing. This is illustrating two geometric ways of visualizing vector addition, and in this case, since we're thinking of complex numbers as vectors, as complex number addition. You've got something called the head-to-tail interpretation of complex number and vector addition. If you take Z1 as an arrow here, this red arrow, and at its head, at its tip, put the tail of this blue arrow, Z2 translated over here, then the head of Z2, we've done head to tail, this head goes with this tail, is going to be at the head of the sum in green here, Z1 plus Z2. Or I could do it the other way, which really emphasizes the commutative property. I could start with Z2, translate Z1 up here so that it's the head of the blue arrow is at the tail of the red arrow, draw that red arrow, and once again, its head is at the head of the sum Z1 plus Z2. It's also illustrating the parallelogram law. This is a parallelogram that you see here. It's a quadrilateral with parallel sides. That's how to add vectors, and in this case, how to add complex numbers. Is this a good idea? Physics justifies this as a good idea. As the most basic application you could imagine, you could think in terms of motion, displacement. If you travel along the red arrow and then along the blue arrow, what is your net change in position or displacement? It effectively is this green arrow going from your starting point to your ending point. And you could do it the other way around as well. Go along this blue arrow and then this red arrow. That's a basic application to motion. Perhaps a more important application is if you think of these arrows as being representing forces. When you add forces in this way, like if you've got two forces acting on an object, the net resultant force is the green arrow that is formed by this geometric method. If I go back to thinking of this complex number addition in terms of functions, once again write w equals f of z equals z plus 4 plus 3i, I could also think of this in terms of a translation of a point, or translations of points, any point that I want. I could plug in z2 into this like I did before, and what do I get? I get the sum z1 plus z2. I could imagine starting at this point for z2 and being translated along this red arrow that is representing 4 plus 3i to end up at this point, z1 plus z2. We're translating that point individually. We could do that for any point in the plane. That's a way to think of complex number addition in terms of functions. As you might expect from the first two videos, I've got Mathematica demonstrations of these things. First of all, the head-to-tail law and parallelogram law. This code generates this visual that you see right here. I can move these locator things around and change what my vectors are, what my complex numbers are. When I move these sliders, those translate the vectors parallel to where they start, and I get the resultant sum showing up. Once I've done the translation, I can do it to the first vector, the blue vector there. I can also do it to the red vector, and I can do it to both, and I see the parallelogram. And it doesn't matter what your starting complex numbers are. The parallelogram law and the head-to-tail law for vector addition still work. We can always find the answer visually. That's what the code that you see right here does. A second bit of code that you see right here helps us think about adding complex numbers as generating translations of a plane, translational transformations, and the code generates three different groups of starting points. The first set of points is in a disk of radius 1 centered at the origin. The second set of starting points is in a disk of radius 1.5 centered at the point -2, 2. And the third set of starting points is in really a square, and that's what you see here. The red arrow represents what I'm adding to these inputs. Think of these as a bunch of different z values, and this is a particular vector. In this case, actually, it's 4 plus 2i instead of 4 plus 3i. And if I move the slider, I can think about translating these points from their starting positions to their ending positions, effectively transforming z values into w values. The Mathematica code allows me to change what the vector that I'm adding is. I can move it over here, for example, and I can translate down this way. And I can do that for any set of points, and I can do it for any vector affecting any kind of translation that I want. That's a nice visual way to think about complex number addition. So, as always, I hope you found this to be interesting, and I end by saying strength and honor to you. Be strong, honor all people, but also be an honorable person yourself. Have a good day.